So for question number 3 with the winch, we're pulling this 250 kilogram block up a 20 meter long inclined plane. Okay, so we know this side's 20 meters long. Okay, we know it's tilted 35 degrees. Okay, above the horizontal, and we're looking for the change in gravitational potential energy that the block undergoes. Again, just like on the quiz, there's 2 ways to do this. I can find all the forces and solve it as like a Newton's second law question and then do force times distance at the end, or I can solve this as a work energy theorem question, which in the end will be less work. All right. It's being pulled at a constant velocity. It doesn't say that, but we have to assume that since it gives us no changes in velocity. Okay, which means that really, whether I lift it to the top of that ramp or push it up the ramp, I do the same amount of work either way. Agreed? It's frictionless, so it doesn't affect me to do it either way. Okay, so if I can find the change in height between the bottom of the ramp and the top of the ramp, can I figure out how much the potential energy changes? Yeah, I have 0 at the bottom. So my final potential energy is my change in potential energy. So I'm going to find the height of the ramp first by going 20 meters, the hypotenuse, times the sine of 35. Okay, because it's the opposite side in this case. So we'll have 20 times the sine of 35. All right, so it's going to end up being 11.47 meters tall. Obviously, we'll keep all the decimals when we're doing our calculations here. Now that I know that, okay, all I have to do is do a final potential energy calculation because the initial potential energy is 0. So M times G times HF. So this is a 250 kilogram block times 9.81 times 11.47 meters, and I will have my answer. So 250 times 9.81 times my answer with all the decimals. 2.81, because we have 3 significant figures there, 2.81 times 10 to the 4 joules. Okay, everybody all right with that? Okay. Again, if I wanted to calculate it the longer way, right, I would do an FG calculation. I'd find F parallel. Okay, I'd multiply F parallel by the distance, and then I would have my final answer, as opposed to doing, so that's 3 calculations as opposed to doing 2 calculations. Right? Okay, kinetic energy. You have kinetic energy if you are what? Moving. Okay. There are only 2 ways to get potential energy. Do work directly on the object or convert potential energy into kinetic. How do you convert potential energy into kinetic? You drop something, exactly. Okay, as long as it's not at ground level, it has potential energy, and as soon as you drop it, it will accelerate downwards. Its height will decrease, its speed will increase, meaning that you are converting one form of energy into another, potential into kinetic. Okay, and the other way obviously is to do work on the object directly. That is, exert a force on it through a distance and make it go faster. Okay, those are the 2 ways you can get kinetic energy. Now, kinetic energy is affected by only 2 things. It is affected by mass and speed. Now, that relationship does not work like the potential energy relationship does. Okay, in potential energy, height is linearly related to energy. That is, if I double the height, I will have twice as much energy. Everybody follow? In kinetic energy, it's exponential. If I double the speed, I have 4 times as much energy. Consider what that means for you when you drive a car. Okay, if you are going 60 kilometers an hour through a 30 kilometer an hour zone, school, playground, okay, something like that, how much further will you travel before you stop than you would if you were going the speed limit? Four times as far. You have doubled your speed. You now have 4 times as much energy as you would have if you were going the speed limit. So instead of being able to stop in 10 meters, it now takes you 40. Is that a significant difference? especially if it's a little kid who runs out in front of you. Okay? Unfortunately, in our current society, people do not take driving as a serious responsibility. Okay? I see it all the time. It's why I take back roads everywhere I can, because I can't stand to be on the road with idiots. And there are far too many of them. Okay? These are the people who, instead of paying attention to the road, are texting, okay? Or are going way too fast through zones where they should be going much slower. Okay? There are a lot of poor drivers out there who do not understand the relationship between what they are doing and what can happen. Okay? Excessive speed leads to exponentially increased stopping distance. Okay? You really have to understand that part of it. And it gets worse with deteriorating road conditions. Okay? If you decrease the amount of friction available, you are increasing even more the stopping distance required for your car. Okay? So please take speed limits seriously, especially ones that are school zones, playground zones. There's little kids. They don't always look before they cross the street. Okay? So always be on the lookout because you're smarter than they are because you're older than they are. Okay? Which means you should be going the speed limit. Same with the construction zone. Okay, there's lots of those. Okay, well, I mean, construction season's winding down because it's almost winter, right? We have 2 seasons in Alberta: winter and construction. Okay, winter lasts 8 months, construction lasts 4 months. Okay, and we're on the kind of tail end of construction season. So you always got to be mindful of that when you're going through a construction zone. There's a reason the speed fines double in a construction zone. Okay, there's people walking around. Right? And you see this on the highways all the time. Okay, it's 50 kilometers an hour and somebody's going 120. Okay, because, well, the signs were 3 kilometers back from where they're working. Okay, and they got tired of waiting. All right, well, that's somebody's dad or somebody's mom that's working in that construction zone. Okay, you got to take that into account. We just don't always think of that when we're behind the wheel. Okay, being behind the wheel is a big responsibility. Now, texting and driving, another one. If you're texting and driving, not only are you worse than someone speeding, you're worse than a drunk. Believe it or not, that's what the studies show. Being a distracted driver is more dangerous than being a drunk driver. I am not saying by any stretch of the imagination that you should drive while under the influence of anything, because that's like firing a weapon in a crowded room. You're going to kill somebody eventually. Okay? You should never do that. However, the difference between a drunk and a distracted driver is that while a drunk driver will react late, they will react. A distracted driver will never see it coming because they're not even paying attention to the road. Now, if you're both drunk and distracted, you should never be allowed to drive again. Unfortunately, there's some of those out there too. So I want to show you just how much of an effect being distracted has on your reaction time. Okay, I'm going to pick on Noah here. Okay, Noah, I want you to put your hand right at the edge of your desk here, okay, and just, yeah, so you're going to grab the ruler when I drop it, okay, so you're just going to kind of be paying attention to the ruler, and you don't want to, okay. So when I dropped it and he was paying attention, it only fell 28 centimeters, okay, before he grabbed it. All right, take out your phone, go on social media, start doing what you normally do, but put your hand out in the same position it was before. Okay, that wasn't bad. That's one of the best ones I've seen. I have had this happen, and people caught it on the rebound. Okay, it fell all the way to the floor, bounced on the floor, and then they grabbed it on the rebound. The only thing that told them that they should grab the ruler is the sound of it hitting the ground. That means your only cue to stop your car is the sound of you hitting something, or, God forbid, someone. Okay? Guys, he caught it at 28 centimeters when he was paying attention. It fell more than twice as far when he wasn't paying attention. Okay? At that speed, okay, whatever speed it is, you just traveled twice as far before reacting. Not good. Okay? Think about it. It's just something to think about. You guys are all old enough to drive. It's a big responsibility. Okay? Treat it as such. All right, so on a highway, we have a car that has a mass of 1,200 kilograms. It is traveling at 20 meters per second and has kinetic energy equal to a loaded van that has a mass of 4.8 times 10 to the 3 kilograms. Okay, what is the speed of the van? All right, kind of a weirdly written question, but something that we can do for sure. So here's what we know. We know the mass of the car, and we know the speed of the car. Okay, we also know the mass of the van. Okay, we know they have the same kinetic energy. So we need to figure out how fast the van is going. Can I figure out how much kinetic energy the car has? Right? I have the mass of the car, I have the speed of the car. I have m and v. So I can calculate the kinetic energy of both vehicles because they told me they have the same kinetic energy. All right, so I'm going to go 1/2 mv squared, and I'm going to solve for ek. All right, so we're going to have 1/2 times 1,200 times v squared. Okay, so 20 squared. Okay, so we got 240,000 joules worth of energy. Okay, before we calculate this mathematically, okay, the van is 4 times heavier than the car, but has the same energy. Is it going faster or slower? How much slower? Okay, twice as slow, half as fast. Whichever, same thing, twice as slow and half as fast. Okay, so let's calculate then the speed of the van. So again, we're going to have EK equals 1/2 mv, okay, mass of the van, times the speed of the van squared. So we're solving for the speed of the van here. So that'll be EK divided by 1/2 times the mass of the van, square rooted. Okay, so we'll take our 240,000. Okay, we'll divide that by half of the van's mass, which would be 2,400 kilograms. Oop. And then we'll square root that. Okay, half as fast. 4 times heavier, and at only half the speed, it has the same kinetic energy. All right, that's something you have to consider if you're one of those people who cuts off semi-trucks on the highway. Okay, because you see people do that, right? They're like, oh, I got to get around that semi. Oh, that's my exit. Right in front of this big, giant semi-truck who has zero ability to change their velocity in the amount of time you have given them. Okay, you have to consider that the heavier the vehicle, the greater the stopping distance. That's linear, though. Okay, it's a linear increase. If I have twice as heavy a vehicle going the same speed, okay, it has twice as much energy. Mass isn't squared, just speed. Okay, so the bigger the vehicle you have, the greater your energy is going to be, and thus the greater your stopping distance. Okay, you can stop a small car on a dime, okay, compared to something larger. Okay, it just has more energy, and so it's going to require longer to stop. Now, it's not always perfectly linear like that. Obviously, larger vehicles will also have larger braking systems, okay, to help enable them to stop. But if it just came down to simple physics, okay, where it was just the friction and just the energy of the car, okay, a twice as heavy vehicle will take twice as far to stop. Okay, everybody with me on that? So consider that, because I saw a guy the other day on the Deerfoot who brake checked a semi. Okay, why you would do that? Okay, I don't know what he thought he was proving, except that he was willing to die to prove a point to the semi-truck driver. Okay, you can't brake check something that big. You guys know what I mean by brake checking? Okay, when you pull in front of somebody, tap on the brakes. Okay, I don't know why people do that, but they do it. Okay, yeah, I don't know why he did that, but like the semi-truck, you could see it visibly wobble, okay, because the driver pounded on the brakes and the trailer started to come sideways. He managed to get controlled. Okay, don't brake check or cut off a semi. They are too heavy. They have way more energy than you. Okay. All right, let's have you try these 3 kinetic energy questions. They're not too difficult, but they all involve 1/2 mv squared. All right, so question number one, I assume everyone's done question number one. The only trick to number one is it asks what's the energy of the system, which means what do you have to do with the two masses? You got to add them together. Okay, so 0.5 times 61 kilograms, okay, and then times 2.5 squared, and you've got your answer 1.19 or 1.91, sorry, times 10 to the 2 joules. Okay, what's the trick in question two? Yeah, you got to convert it to meters per second. Okay, this is again where when I told you what the units for joules were, that's why I tell you that. Okay, a joule is a kilogram meter squared per second squared, not a kilogram kilometer squared per hour squared. That's not a joule. All right, so we need to make sure that our units match what we're going to try to find. So you do have to convert the 80 kilometers per hour to meters per second by dividing by 3.6. Okay, then it's just a matter of solving for mass. Yeah, on that one. Okay, how many people have done number two? Okay, so how many people have done three? Okay, let's go over number three here. Okay, the way they've written number three, I would write it differently. I would, in number three, I would ask, what's the height of the ramp? Okay, that way I turn it into not just a change in kinetic energy question, but a conservation of energy question, which is what we're leading into later. Okay, but for right now, we'll solve it the way they have it. Okay, we're looking for the increase in his kinetic energy. In other words, we're looking for the change in kinetic energy. So that's going to be 1/2 mvf squared minus 1/2 mvi squared. Okay, so we'll have 1/2 times 65 times 4.2 squared minus 1/2 times 65 times 1.75 squared. Okay, when we do that, we find that the change in kinetic energy is 474 joules. Right, so that makes that question fairly simplistic. But now if I ask you, how tall is the ramp? What do you have to do? Okay, add it in, like how do you mean? Okay, I would even make it simpler than that. If this is the change in kinetic energy, it's also the change in potential energy, right? And when you're going down a ramp, you're converting potential energy into kinetic energy. So this is the change in kinetic energy, or sorry, potential energy as well. So if we're just assuming top of the ramp to bottom of the ramp, which is what we'd be assuming, he has no energy at the bottom and 474 at the top. Okay, so all we have to do then is figure out how tall the ramp is. It's not exactly true because he was moving at the top of the ramp. Okay, we'd have to go a little more into it than that, but we could figure out essentially how far down the ramp he went during that time, because this is change in kinetic is also the change in potential. So we could calculate what his change in height was during this by simply doing, okay, and solving for h. All right, we just add one more step. All right. Okay, I want you guys to try 2, and we'll just do 2 for now, and then we'll talk about number 3 after that. I'll make it bigger so you can read it. All right, so question number 2 is basically asking you which is more important, mass or velocity in terms of kinetic energy. All right, that's kind of what number 2 is trying to demonstrate to you. So give that one a try. Okay, so for a question like number 2, if I was to ask something like that, it would be a written response question, and I wouldn't necessarily expect to see any math. Okay, you could certainly calculate the kinetic energy of this ball, and then calculate what 1/3 of 1.5 is, and double the 550 and redo the calculation. But okay, that's a lot of work to prove this. Okay, if I just make everything for canon A essentially 1. Okay, so I'm just going to say EK equals 1/2 mv squared. I'm just going to say 1 and 1. I get a kinetic energy of 1. Okay, and I know where you're thinking it's not 1 Coderre, but I'm just trying to show you how much the factor of increase here. Okay, in the next one, it's going to be 1/3 times, and we're going to double the velocity, so that's going to be times 4. So that'll be 4/3. Is that greater than 1? Yeah, I have 4 times the energy due to the speed. I have 1/3 the energy due to the decreased mass, but that's still more energy than this ball. Okay, because speed has a bigger effect on energy than mass does. Remember, speed's effect is exponential. All right. So if we're looking at this situation, not like firing a smaller cannonball could actually result in more damage simply because it would possess more energy upon striking the structure. Okay. This is the idea behind the railgun. How many people have heard of that before? Okay. It's kind of out of science fiction, but the idea of a railgun is you use a really small projectile, but you accelerate it to like unbelievable speeds using electromagnetic force fields. Okay, essentially. So you have you don't have to carry explosive munitions in a ship anymore. If you have a railgun, you simply use the kinetic energy of the projectile to do damage. Okay, and you can do a lot of damage because it's moving so fast. Okay, its kinetic energy is unbelievable, and as a result, it can penetrate layers and layers of armor, okay, through tanks, through naval vessels and whatever, just because it has so much energy. It doesn't have to explode in order to cause damage. Okay, traditional munitions, they are a high-speed, high-explosive projectile. Okay, they essentially depend on the chemical reaction to do most of the damage. Okay, with something that's just a kinetic energy weapon, then they have an incredibly high speed. Okay, and they rely on that to do their damage instead. Okay, now that's better if you're on the ship that's carrying the non-explosive munitions, because if you get hit, there are no secondary explosions. Okay, that's usually what destroys like military machinery, is they get struck by something and their own ammunition explodes. Okay, what's that? They're being developed. Yes, yeah, they have prototypes that they have. So the idea there is you would have no explosive munitions on board your vessel or tank or whatever, and so if you got hit, you wouldn't have to worry about your own ammunition killing you. Okay, which is inevitably what happens. Okay. All right. Now, for this one with the Meteor Crater, okay, so we're looking at this here. We know that the meteor that caused that crater had a radius of 40 meters and a mass of 2.6 times 10 to the 8 kilograms and struck the Earth at 7.2 times 10 to the 4 kilometers per hour. What do you have to do with that number? Right, divide it by 3.6 in order to get it in meters per second, and then solve A and B. All right, so give number 3 a try there. All right, so in part A of number 3, they want to know the kinetic energy of the meteor at the instant of impact. So all we have to do is go EK equals 1/2 mv squared. All right, so we're going to 1/2 times 2.6 times 10 to the 8 kilograms, okay, times the speed, which we have to divide first by 3.6. So it was 7.2 times 10 to the 4. Okay, so we got 20,000 meters per second here, okay, as our velocity. So we're going to take that answer squared, okay, and we're going to multiply that by 0.5 times 2.6 times 10 to the 8. All right, so we got 5.2 times 10 to the 16 joules of energy. All right, that's a lot, okay? It's a lot of energy. And now we're comparing it to how many tons of dynamite that would be equivalent to. That's how all explosions are measured, okay? So like nuclear warhead yield is always measured in tons of TNT. The scary part of that is that we usually measure that in megatons, okay? So if you have, for example, a typical nuclear weapon, it could be in the like 2 to 3 megaton range. That's 2 to 3 million tons of dynamite, okay, in one bomb, which is why they're so scary. Okay, so this particular comet, when it struck the Earth, okay, if we just divide this here by the amount of energy in 1 ton of TNT, so divided by 4.6. Okay, so that's 11,304,347 tons of TNT. So somebody piled up, okay, 11 megatons of dynamite on the surface of the Earth and blew it up. Okay, that's what that meteor did. Okay, that's the equivalent amount of damage that meteor did when it struck, which is why it cut out a crater like that. Okay, it's pretty big. It's several kilometers across, I think they said, right? But anyway, it's huge. Okay, so imagine the one that like hit in the Yucatan where it ended the dinosaurs. Right? It was even bigger than that. Right? It's a lot of energy. There, I'll just rock you to sleep tonight with that thought. Okay, yeah, you can, yeah. Okay, that one we don't have to do. Okay, so I want you guys to go to the dynamics workbook because now I want you to work on the energy questions that were after the work ones we did yesterday. Okay, so you're working here, guys, on page 6 on these energy problems here. Okay, they are similar to what we've been working on, but are more energy as opposed to work focused, but there are going to be some that involve both. Right, gentlemen? Okay, get to work on those. So the trick to number 2 is you're given 2 distances. The spring is initially 20 centimeters long, and then I compress it to 13.5 centimeters. Over what distance did I exert the force? 6.5. Okay, usually people use the 13.5, but that's how long the spring is now, as opposed to the distance I exerted the force over is 20 minus 13.5. Okay, so it's just 20 times 6.5. Okay, and that will give us actually 0.065. Okay, because it's in centimeters, has to be in meters. Okay, and that'll give us our 4.2 joules. So there's a metric conversion that has to happen to meters, and then we have to realize that the force is only exerted over 6.5, not 13.5 centimeters. Yeah. Okay. And the other one's giving us trouble. 4. Okay, so on number 4 here, we're pushing this object to the top of an incline. The force being applied along the incline is 600 newtons. What's the potential energy of the object when it is at the top of the incline with respect to the bottom? Okay, since they don't mention friction being a factor, we're going to assume it is not. Okay, all I'm doing here is changing what kind of energy? Potential. Okay, it also mentions nothing about me accelerating this object in any way, shape, or form. All right, so what I would do here is simply take my mass, 200 kilograms, times 9.81 times 6, okay, and I should get 1.2 times 10 to the 4 joules. All I'm doing is changing the potential energy from the bottom to the top, okay? So we have our 200, okay, times 9.81 times 6 meters, okay? Whoop. Yeah, that's right, 1.2 times 10 to the 4, yeah, okay. Everybody with me there? Okay. Yes, you could find F parallel and you could multiply it by 12 and do all that kind of stuff, but again, it takes longer. Okay. You'll arrive at the same answer, but it takes longer. Because you would also on this one have to find the angle because I didn't give it to you. It's 30 degrees. But okay. All right. Any other ones? Okay, keep going then.